now, and ChatGPT certainly wasn't a thing. But anyway, you build a Fourier series, which is wonderful. And I don't have to tell this audience, you extract, that's in the time domain, you extract out in the frequency domain, you extract out all the frequencies, and you get these beautiful spikes, and you can see all these things. And so I will get onto this. I can't remember how I've done this now, but it's fine. You won't mind if I jump a little. But actually, I think I did it all together. So I know how to do Fourier analysis. And then when I moved into finance, so it's a little bit jumping around, but you can just see. So this was the main thing I would say that I learned from my masters was this technique. There are cycles in finance all the time, right? There's a business cycle and all over the place. There's GDP cycles, there's credit cycles, very noisy, of course. You get COVID superimposed. You get COVID superimposed on these things. Obviously, that's an outlier, but again, you have to know how to deal with that, how to clean data and so on. I don't have to tell physicists that. Maybe theoretical physicists. Practical physicists, you've got to clean a lot of data. And I mean, the same is true in finance. It's very noisy data. Remember, in finance, you are dealing with human beings, sadly. And the way we are irrational, we make weird decisions, and people overreact, and you get the picture, right? So you've got to deal a little bit with how the humans react. But there are these broad cycles and smaller cycles superimposed. And I should have said this at the beginning, so I feel a bit bad now, but I'll say it now. Throughout this, I mean, I might make the odd joke, but I'm not disparaging finance or my colleagues in finance at all, right? They're just taught differently. We are taught differently. I mean, I remember when I did, I switched over, you're not taught as much mathematics at all. And I think that's very sad because there's obviously, applications for mathematics. Let's call it that rather than physics. But, you can't speak physics if you can't speak. You can't speak physics if you can't speak maths, as you know. So please don't think I'm disparaging anyone. It's just we're taught differently. And no one is taught this in finance, believe me. Or as far as I know, in South Africa, and I teach at a few universities in finance, not in econometrics either. So, when you come along and you say, oh, yeah, there's a way to extract, because someone will say, wow, that's nice and cyclical. I think the period is about, and you go, there is a way, there is a mathematical way. And, you are suddenly, people think that you could walk on water. It's wonderful. So that was just one simple application, which when I flipped over into finance, as part of the story, it was just because, immediately you recognize that. Whenever you see a cycle, noisy data, you know that you can apply Fourier, and it does. It works brilliantly. It keeps getting stuck, I'm afraid. What do I do?
No, that's my mistake. Sorry. I had to,
no. Just move it there and then, okay, cool. So, I mean, just more of the same. This is log growth rates of GDP, and it's just different types of filters, the HD filter, whatever. You apply these things, you put the smoothing things on, and then you run the Fourier and you get out these beautiful results. And it's just, as I say, it's spectacular, right? You get out your spikes, you ignore the noise, etc. You decide on a threshold and you can move on. And it's proved to be very, very effective. I'll probably show you some, I think I do. I've got some examples later on. A student of mine he was writing a paper on, all my students on our finance, finance. And he was looking at commodity prices, and silicon and uranium and all that sort of thing, they're not really cyclical, although there might be a broad sort of superimposed. But he was also looking at crops, coffee and etc., which obviously are affected by the season, so you have to extract the seasonality. But also he found this very anomalous, well, to him, bless him, weird sort of cycle. We were running Fourier through it, and he picked up a 1 in 7 year cycle. And you go and look at what's that thing that affects South Africa's weather, El Nino, which is every 7 years, whatever, something like that. And you look at that frequency, and I mean, you can explain these things. It's just wonderful. So, but I think I'll show you that example a little bit later on. So, having studied big things very far away, I and my father looking disparagingly on my research, I decided, still at the University of Natal, to go into little things very close up, as in plasma nuclear physics, right, at the Heidelberg Dam, the Atomic Energy Corporation. And they had this is, again, I don't have to tell physicists this, but we were working on fusion, which that's fusion 101. you know, you pump these two things in. This requires a lot of energy. Remember, these are positive nuclei, so that strong forces repelling them. But if you can overcome that with enough temperature and whatever, it's not an accelerator. I probably don't have to tell you that, you know, the machine is probably about the size of this room, and it's not an accelerator. But if you can get these things up to high enough temperature and pressure and so on, you know, theoretically you should be able to get them to fuse. Off goes harmless helium, not radioactive at all, and some energy coming out, thermonuclear neutrons. And the idea is, if anyone's following nuclear fusion, you'll know it's not science-fittingly funny, but the joke that goes around since the 1960s is that we're going to have nuclear fusion in 40 years, and we're still saying it. Although there's been some very good advancements in the last few years, well, last few months actually. So we live in hope, but we haven't got there yet. We have not perfected nuclear fusion, as you know. It would be headlines. I mean, we basically solved the energy crisis, but there's a long way to go. You know, we've got to prove it's scientifically possible first, and we're almost there. Then we've got to prove that it's, you know, engineeringly feasible, because these machines are complex and expensive, and they need a lot of maintenance. So, you know, is it going to be worth it, etc., etc. But still, research continues. And
what are those developments that you think past few months? Is that easy to explain or not really?
No, all I know is that they're getting much. You'll see a figure in a minute of, you know, as the graph sort of, as we're approaching the sort of fusion limit, and we're getting, I don't know what they've done differently, but they are getting very close. So we live in hope. We live in hope.
I think that recently, first time, or I don't know, or however long, like a minute or something, the Tokamak or whatever, you know, the inside the chamber, there was a net energy produced out of that.
Okay. And that's sort of the way to do it. The analogy that I usually draw, I don't have to do it for physicists, but, you know, if you held a match, you know, under a piece of wood for a couple of seconds and you take it away, the wood's not going to current burn. And we'll get fusion when we can take the external power source away, and there's enough fusion energy to keep it going. So in case, oh yeah, that's E equals MC squared writ large. It's just, that's also wonderful. So very quickly, we're not here to do, of course, some tokamak physics. It's called a tokamak. It's a Russian word. It comes sort of from those, it's toroidal. You can see it's sort of like a donut. Where is a donut? And it's got magnetic fields and colloidal fields and all sorts of fields and whatever. And you can see it's not an accelerator, as I say, about the size of this room. We have one in South Africa, sadly no more. But you pump the plasma in there, you basically pump deuterium and whatever in there, and it's basically a vacuum. So to get temperatures up very, very high is actually quite easy. We were getting, you know, with the you know, nuclei of hydrogen, you can easily get it hotter than the sun easily, because it's basically a vacuum. And there's a thing called the Lawson criterion, which is the product of how long you have it at that temperature and at that pressure. You can't just keep pumping, you know, ions, these ions into there, because then the reaction becomes sluggish. So you've got to balance it out. But the product of the temperature, the confinement time, and the density of these things, that's called the Lawson criteria. And when you pass this threshold, which I think it's on the next slide, or the next one, you'll see we are close. South Africa's tokamak was quite a way off, right? Okay, anyway, a small little tokamak. It was the Atomic Energy Corporation. I will tell you straight, it was one of the best jobs that I ever had in my life. Just working with scientists like that, who had senses of humor like mine, was just wonderful. It really was my best job. If there are any of my colleagues listening online, I hope they remember that. Actually, one of the physicists came to Wits in those days to teach. I mean, it closed down in about early 90s to teach. He went to finance. So I'm not the first. And in case for the foreigners here who don't know why the hell this talk was called Tokoloshe, like why the hell is that in there? You can see the name. That's what this fusion device is, right? And so in South Africa, it was just begging for the name, because they've all got names like Torture and Tech Store and all these, you know, acronyms and so on. And in South Africa, in case you don't know, and if you don't, you should, there's a little thing called Tokoloshe, which looks something like that. And South Africans know this, right? And you can see this creature attacks you at night. So you put your bed, and I'm not sure, it's legend. put your bed up on bricks so that the Tokoloshe can't get to you, although that's a very low bed. But that's the idea, right? So that's where we got the name from, just because the first three letters are the first three letters of Tokamak. That was not ours. It's just another picture of one. As I say, you can see it's got an accelerator, but a very complicated machine, right? So back onto, so there's this Lawson criterion that I was telling you about. You can read this sort of stuff. Net energy is achieved, so net output of energy when this fusion production obviously is greater than energy losses, and so on. And you can see the confinement time and the energy density and so on must be a certain level. And that's where we were. So quite far off. This is, I think that's a German one. I'm not going to go through all. JET is in the UK, near Oxford, Joint European Torus, and so on. This may even be, and you can see reactive conditions are up at the top there. ITER is the international.
The one in France, right?
Yes.
It's yeah.
I mean, we're getting there. You can see we whatever we it was a long time ago. We were doing interesting edge plasma physics, all sorts of things. But we are getting to this ignition temperature, and who knows what's going to happen. Anyway, that was my sorry.
I mean, since so you've got this plasma in a vacuum, and you're just heating up water. Are you actually using the plasma to heat up the water? Or is it kind of inefficient? I mean, the way it works is you heat up water, and that drives a turbine, right? You know,
Oh, ultimately.
yeah, ultimately,
Yeah, that's.
I mean, how do you got this hot plasma in a vacuum?
No, you get fusion.
In,
I understand, but how do you extract the heat from that?
From the fuel. What do you mean? Like exhaustion?
Yeah,
It's something called.
but it's you've got it in a vacuum. I guess it radiates.
Yeah.
Kind of inefficient.
No, you're not. It's not the convection. I mean, like it's the radiated energy that it's.
that's when we're going to hand it over to the engineers. Seriously, and say, okay, we've done it now.
Water around and stuff. It's
Yeah.
natural, the radiation.
But it is going to be thermo. You know, it's going to be heating up water ultimately. So it's very after this very advanced thing. But whatever. There is, as you can imagine, there is endless, not endless, but pretty much endless energy for this. I mean, it's water, at least. I mean, it's hydrogen. So so we've got a lot of fuel for this. So anyway, and it's it's clean, allegedly. I'm sure no one will use it for non-peaceful reasons and so on. So whatever. But anyway, we were doing this project and see what the next slide is. Oh yes. So just to put it in context of where the hell, what was I doing? That's a slice through it, and these are magnificent pictures. I wish I could have got hold of when I was doing my work. But the plasma, because it rotates and it's got colloidal velocity and toroidal, and it radiates outward. All these, the plasma sort of radiates outward at a certain speed, and you can imagine when a hot, supercharged, this plasma touches the metallic boundary, there's what we call a discharge, and it's that's the end of the plasma burst. And it was how can that's obviously restricts that confinement time, right? So we were getting 30 milliseconds or 40 milliseconds if we were lucky in those days. And you need for that Lawson criterion. I'm going way too much into the physics here, but for the Lawson criterion, you need about 3 seconds. You need about 3 seconds of sustained fusion. Because fusion is happening, it's just not enough to be self-sustaining. So we were, as I say, we were only getting about 40 milliseconds, and then the whole plasma became unstable. So I had a thing called the Langmuir probe, which you stuck in the outside, and you measure these radial and toroidal velocities, and you calculate shears and all sorts of things, which I would love to go into if you ever need another speaker. I'm joking. But that's what we were looking at. And the reason I'm telling you those details is for this figure, not because I'm going to go into very much detail, but because you've got vector field, basically. You've got electric fields. You can imagine there's this the magnetic field on the outside, which is keeping it into the middle. You've got these, we had coils around the with a certain helicity around the machine. So we were locking. You get these magnetic islands that form, and they rotate toroidally. And if you switched on these coils at the right time, whatever, you could simulate the same magnetic structure on the inside, and this sort of rotating plasma sort of bounced, and we could freeze it. And that did extend the confinement time, and we got very excited. And of course, I had my, it's still, the plasma particles were still radiating outwards. So that's essentially the gist. But this is important. I was dealing, you're dealing with vector fields, right? There's things going in all directions. You have to calculate magnitudes of these speeds and all sorts of things, but it's vectors, right? Which we know and love. Not so big in finance. And I often, when I give lectures, and I say to people, you do remember vectors and scalars, and you get a blank look. And I say, well, we are going to do that. We're going to do Pythagoras. We're going to do the cosine rule. You thought it was all behind you, but it's not. So that's the sort of background there. And I don't have to introduce you to the wonders of, three-dimensional, n-dimensional vector. The way vectors add, right? We all know how they add. They don't. It's not an arithmetic thing. It's a vector. This will be important later, right? Because believe it or not, there are endless applications of vector addition in finance. And again, not disparaging anyone, but even textbooks. I'll get to that point, but you're just given the formula and you're told, if these are the little components, you put these things into a little portfolio. There's the 3 different shares or whatever. And you don't want to calculate, what the standard deviation or the volatility is of each component, but you don't want to know that. You want to know, portfolio. And you get given this hideous formula that people think it's hideous, and I've never seen an explanation of where it comes from. It's just like, well, that's what it is. Do this, and you just sort of think, that's just the cosine rule. It's like it's vectors. And that's why, as I say, I'm not cleverer, none of us are cleverer. We just taught differently. You can stop that immediately. It's like, well, that's just, it's just the way vectors add. And when you see that, so often I give lectures in finance, and you get your props and you say, okay, this is the origin, and you go off into 3 dimensions. It's wonderful. But it isn't taught. And I do believe that when people see it, when people see the 3 dimension, this is the way things are adding. This is how diversification comes about. Because people, it's hard to visualize. You're putting a really risky stock with a really non-risky stock, or 2 very risky stocks, and you put them in the same portfolio, and what comes out? The portfolio volatility is less. Like, how can that be? Of course, it's diversification, because they're anti-correlated. And you can have it with N stocks and so on. And that's a really difficult concept for people to visualize if you're not thinking vectorially. So that was something I think I benefited from. We'll talk about a little bit about that later. This is probably more maths and physics. Cubic and you often get like those observations I was doing of the luminosity of the stars. You get point data, right? And often you need it to be a little bit more granular than that. It's not going to be these linear. We're way beyond linear interpolation, and there is a way to do cubic interpolation. And a number of times I've been in finance. Actually, once it was just the Lord delivered it into my hands. There was a conversation going on next to me, and the one person said to the other, wouldn't it be nice if we didn't have to join these lines with straight, because jokes aside, I'll tell you more about this in a minute, but this is like a yield curve, like interest rate curve. So this could be the 1-year rate, the 2-year rate, the 3-year rate, etc., etc. And you only get node points, right? You don't get a 1-year and 1-day point, or a 3-year and 17-day point. You get a 1-year point, a 2-year point, a 3-year point, and so on. And there's big gaps in between. But what if you've got an instrument that matures in 3 years and 14 days? What the hell? And you'd be surprised. You might think, oh, it's going to be a small amount. But when you're dealing with billions of currency amounts, I mean, it's really substantial. You have to be very careful about the way you interpolate these things and so on. And if you this is an extreme example, but if you join that linearly, you can see how inaccurate you would be, because that's not the way it is, right? And again, I'm sure you all know your cubic interpolation, and I'm not going to go into all these. I'm just going to. So actually, you know what? I'm going to go back here. Yes, you can have N, of course.
I just think going to do parabolic quadratic interpolation.
Indeed, but this is just for example. But when you've got a yield curve with 13 node points or something, and each one has got a cubic polynomial. And you've got, 4 coefficients there that you don't know, and your 4 equations essentially are, that point, that point, that point, these coordinates, that's whatever. That the slope in and the slope out of that point, so that the slope of this cubic polynomial at that point must be the same as the slope of this cubic polynomial going in, and the second derivative. And again, when I'm trying to explain this to non-physicists, you use, it's a wonderful example. You say if you're in a relay race, you have to be in the same position. You have to be moving at the same speed. You can't just be in the same position if one person's traveling at the speed of light and you're like trotting along. And the third thing, your accelerations have to be the same, right? You can be in the same position at the same speed, but if they are accelerating and you're decelerating, you just happen to hit the same number at the right time. You're also not going to have a smooth passing of the baton. So I try to use physical principles. This will come in. I mean, I've basically told you what I use it for, but it'll come in a little bit later as well. So those are the equations. And then, please don't ask me too many questions on this. I did it a while ago, but the wonderful Kalman filter. If you've, it's more of an engineering thing, but of course there's applications in physics. Essentially what it, and again, I'm going to show you the application to finance, believe it or not. They used it originally for firing missiles, but they still do. And it's Bayesian statistics basically. There's a feedback loop, and I think the measurements get more and more accurate, and it sort of says, okay, the plane is moving in a certain way, and the missile's exploding. Let me try and give that an example. So the plane, let's say we use the missile example. The plane or the object, the target, has to be moving in a certain way, right? It can't be moving randomly because then no one on Earth is going to figure out how to hit the damn thing. So it could be moving straight up, it could be moving in a saw shape, it could be oscillating. I mean, it could be, as long as there's a pattern to it, right? And you don't know, so you fire your missile and it explodes. And by that time, the plane is, let's say, moved to a different position. And essentially, I'm really dumbing this down, apologies. You get you try to minimize the variance between where the bomb exploded and where the plane is moved to. And of course, you've got 3 dimensions. I'm talking about just 2. And you feed that back into the system, and it learns. It's the origin of, it's the early sort of ruminants of AI, I suppose, machine learning, Bayesian statistics, and it tries to minimize that variance. And you can watch it. I mean, you can build this in Excel. That's my preferred domain. I'm old school, and you can see it learning. It takes about 36 points depending on what you're using, and then it sort of figures out, okay, the plane is moving in a sinusoid, and then it figures it out and it hits the plane. And it's, as I say, I'm giving a very heuristic, hand-wavy argument here, but essentially you're minimizing the variance between the object, and you'll see the applications finance in a minute, and the target. And as I say, it's feeding back. The next step depends on what happened before. And I don't have my phone here, but the little blue thing on your Google Maps thing, that's all Kalman filter. And they got to the moon as well, which is why this is a relevant picture. Using the Kalman filter, there's it's got to do with predicted states and optimal states and measurements, and you combine these, you assume normality, normal distribution of these things, and you combine them. Kalman was a Russian guy. They do produce brilliant mathematicians and physicists. He was an engineer though. And you combine these and, you get the Kalman filter. So I did a little bit of work with that as well. And then, as I say, when you move into finance, so now you've got, and there's a lot of other applications, of course, but we've only got, so much time. And so, as I said, I didn't plan to go into finance because then suddenly this happened. So it was 1994 in South Africa, turbulent time, and there just was no money, and there was just no money for physics sake. That's probably not true because universities continue, but research for research sake, put it that way. And I mean, this was purely I won't say a vanity program, I hope it wasn't that. But I mean, we were just a bunch of scientists getting paid quite well to do science out of the Atomic Energy Corporation, and it was tragic. It really was a traumatic time in my life. Someone literally walked into the room where we had the Tokamak and switched off the lights, and that was the end. That was the end of the project. There was just no more money for this. So we all got retrenched and scattered to the winds, and that was the end. That was the end of my physics career. But they weren't that cruel. I mean, people knew people, and they said, "Well, there's someone in finance." And yes,
You really good question. Did South Africa actually exploded an atomic bomb?
I'll tell you, but then I have to kill you. No, actually, all right. This is a good story. So if they did the Atomic Energy Corporation, and this is long past history, so I can tell you this. In the building next to ours, where we were on the Atomic Energy Corporation, so I used to run at lunchtime, and we would often come across weird little. I mean, do you know that? Do you know that Hanbias word? It's openly ground.
Next are the research facility. Have you seen it? Yeah. It's still there.
On the slopes. Yeah, they're still doing fission and research and purifying stuff, but not fusion cells.
So, you take the very flexibility on the line in the pre-sub in the international community agreed on this and frequent severe sanctions in the case that case was
But it is well known that they built six. They built six, not a difference. And so my personal story used to, as I say, myself and a colleague, we used to go running in the grounds, and you would come across weird things like this windsock. You know what I mean? You used to think, isn't that for planes? There's no planes that are allowed here. I mean, it could be in it. But there were a few weird things like that. And this is a true story. I promise I'm not making it up. In the building next to ours, we were told that that's where they housed the weapons. I'm sure they did. And literally, the building next to us, we knew nothing of it. And downstairs, they had these cages, sort of like a tesseract, you know, the four-dimensional thing. I'm not kidding. With the, with like a cage on the outside and these radial bars into the inside with a smaller cage in the middle. And that had a little latch, and you could put stuff in there and close it. And that was so that if, there's multiple of these things. So if you were wheeling fissile material past someone else, it guaranteed that you stayed, that distance apart, so you didn't set off a nuclear weapon. And we saw those things. And that's when you realized, gee, that was going on next. So the short answer is we probably did. But it was so top secret, I'm not kidding. I was in the room, I was in the offices next door, and we never knew about it until after it was decommissioned. So, yeah.
Where is it?
It was
Early 80s.
no, it was after 1990. So the private government voluntarily decommissioned it and encouraged by American who didn't want to see the ANC government having things.
Already. Yeah. That was out of the Atomic Energy Corporation. So, okay, so after that, we were scattered to the wind, and I've given you some of these stories anyway. And yeah, this was this paper that I wrote with this one student of mine. So he was looking at nickel, and nickel has this particular frequency, and you can't just superimpose a frequency. Trust me, it's more involved than that. We don't just superimpose a cycle that we think is there. But and he found a reason for this. And it was not nickel, but there was another metal that's used in wars, and you could just see, wars, please God, they're not cyclical. But you could just see whenever there's a war, there's a spike in these things, and he was picking up these things anyway. And I'm not saying nobody, but very few people in econometrics or in finance, they probably know about it, but you could build this thing in Excel for heaven's sake. How difficult can it be? And you get out the nice little Fourier, the amplitude, you pick out your little frequencies, you ignore that, as I said earlier, and you get out these things. This was the El Nino, with lovely cyclical, these nice bursts superimposed on the cycles of the rain, just seasonality. And he was his supervisors were incredibly impressed with that, which is no, South America, I think. Yeah, El Nino affects them more than it affects us, but it does affect us as well, as you know. And then and this is something students do have to know the normal distribution in finance. Although I will tell you this story. And again, this probably I am being slightly disparaging, but it's not of my colleagues. It's not of my academic colleagues. And I shouldn't be so unkind. But I was working at a major asset management place, and we were and essentially what this is, you use normal distribution for a lot of things, but the one big thing we use it for is we assume that the returns, so the percentage price changes on stocks and commodities and things like that, are normally distributed. It doesn't, there's all sorts of things why it's wrong, but people are lazy, so we use it. So this is a very common figure in finance, right? And this was a well-known, very prominent, very smart. I'm not at all saying he's not smart. But it just goes to show the level of understanding. There was you'll see in a second, there was absolutely no understanding of what this word volatility meant and what he was dealing with. And he was a good asset manager. You sort of need to know what volatility is That is your, there's the return component and the risk component. That's the risk component. And I was sitting next to this person, as I won't mention the institution, but and he was really he was a very smart guy. And he turned to me and he said, I said, oh, the volatility last month was XYZ. And he said, does the volatility change? And you could see he had no clue. It was ignorance rather than stupidity. He had no clue that data come in all the time. And I'll tell you one other story while I'm on a roll here. I once asked a colleague, and this is totally disparaging. I said to them, how many data points did you use to generate this normal distribution? It's not 200. 2. I don't even know what the standard deviation of 2 means. You'll get a number, but I don't know what. And that, but again, that's it's beyond stupidity. It's like you have no clue what they're doing. And I've mentored many people in finance. This I do pass back to universities, our education system, and they sat down and gone, is that what you use the normal distribution for? So we really do need to make things more practical because they learn all this, this stuff, and there's no practical stuff. Anyway, profits and losses, and if you take the daily profits and losses on an average stock over extended periods of time, it's roughly 0. It's not exactly 0, but it's roughly 0, the daily returns. So those are profits. These are losses, and you go a certain number of standard deviations, you know what's in the tail here, and you have it cut off. And it's a common thing in finance, you keep this amount of money, because that's all profits, right? That's your bonus. This side is what you lie in bed at night with big bug eyes and you worry about, right? So you need, and you can't protect, we all know this goes off to infinity. You can't protect a portfolio 100% unless you keep exactly the amount that you've invested, which is just not profitable. So you have a cutoff, you have a threshold, which is usually predetermined, the regulator tells you what it is, and you need to keep this, these are all profits and losses, as I say. That amount of the loss, that you keep, all else being equal, this repeats itself. If you've got that amount of money in a suitcase under the bed, you should be able to absorb those losses and the bank can carry on going. I'm really simplifying this, but that's basically the idea. And that's called value at risk. And this here, it's unprotected, right? You cannot keep, I suppose you could get insurance, there's other ways of dealing with it. But anyway, this is called value at risk. It was the subject of my new master's. I've supervised 100 projects on this, right? And all sorts of things. Of course, it's a frequency measure, it just tells you how often you're going to land up here. It doesn't tell you when you do land up there how bad it's going to get. So there's another debate rage. But anyway, and oh, 2 point, this is 5, wait, 1%. So 2.33 standard deviations. Is that what you wanted?
Yeah.
For credit risk, it's not a normal distribution, but that's 99.9%. So and that's for annual losses. And theoretically, I've got to tell you the story. So theoretically, those losses that happen in that tail should happen once in 1,000 years, right? But I had a very dry sense of humor, Scottish boss, and he was not quantitative at all, of his own admission. And he sort of rubbed his chin one day and he said, so it should happen only once every 1,000 years, yet it seems to happen like 3 times every decade. And he was making, people are unpredictable, right? That's my best guess for it. We've got all sorts of economic theories about how, thinking fast and slow and all these weird things, but at the end of the day, you're dealing with humans. So that's the normal distribution of one asset, right? You put them all into a big portfolio, and obviously banks have got thousands of these things. They're all offset and they've got correlations and whatever. And the question is, I don't want to know this thing's volatility. I want to know the volatility of the whole portfolio. And so that's the if that's the distribution of the portfolio losses, then that would be, the volatility of it. And they are given that formula. I mean, this is just for 2 assets, right? You can extend it to N. And I encourage you, if you have nothing to do on a Saturday night, get hold of an economics or finance textbook. You'll come across that. It's risk, right? It's the other dimension, risk and return. So it's a huge part of it. What's that? Exactly. And you sort of look at it, and everyone's and people go like, but why is it like that? And they go, well, just learn it. And it's like when you go out and your mom is cold. Sorry, I'm not trying to be sexist, but you're not cold, but your mom is cold, and you say, but why must I put on a jersey? She's just because I said. And just believe it. And it is incomprehensible. What the hell are we doing? We're multiplying and squaring, and then we've got 2 of this, and that's a correlation and so on. And as you observed, it is just vector addition, where the cosine, of course, and I don't have to tell you this, is just the projection of that onto this. So how much of that is in that direction. So that's why that correlation term is in there. And as I say, I've spent years with props showing people this is the way vectors add. And suddenly you can see, and also, I mean, I can't go into more than 3 dimensions, sadly, but you could picture, you start at the origin here and you go off and, you're adding all these things with different weights, because the weights you can control, the volatilities you can't. And obviously the correlations you can't, the historical correlations. And if you imagine that this is multiple dimensions, you show them, okay, well, depending on how you adjust these weights, and that's just how much you invest in that stock. In principle, you could land up back here, and that's, well, sorry, this is the origin. So, the resultant could be this incredibly tiny little volatility, whereas you've got all these risky things, you get the picture, right? And it's very hard to imagine that without vector addition. And they do always complain, but I say we're not going to do freaking vector. It's the cosine rule. As I say, that there's usually gasps of disbelief because it really is not complex. I mean, it's vector addition, and it makes that formula, especially when you have n dimensions. So they usually just there's this sum I does not equal I equals j from to whatever the number of things in your portfolio omega I sigma I, and that takes, and here I does not equal j. And whatever, they do the summations of the terms. So it's even more condensed. And people just completely freak out. I mean, not everyone, but people have not been taught to think this way. And so that is this impenetrable thing that, what the hell is going on there? And also, we've all heard about derivatives. To my shame, I don't know who it was. Who was the physicist? One of them was a physicist, Black and Scholes. They won the Nobel Prize for it, 73. And they solved this complicated thing with derivatives are just wonderful things. I'm sure you've all heard of them. Somebody called them weapons of financial mass destruction. That was Warren Buffett, and he would know. But they can also be wonderful things. But they've got their complex. They've got partial derivatives, and you throw that at the average person that hasn't dealt with partial derivatives, and it's a problem. But anyway, it was a physicist that actually solved the thing. They got the Nobel Prize for it, and we don't have time to go into it, sadly. But the 3 components of the solution of this partial differential equation to work out the price of what a derivative should be has got, I'm not kidding, and it's a purely financial thing. It's got a convective term, conductive term, and a radiation term. It's just wonderful. It's the heat equation. Exactly.
But I mean, the assumption that the noise scarcity is terrible.
Oh, yeah.
And one of the two lost a lot of money testing these equations.
Absolutely. There's a website, which again, if you've had nothing to do on Saturday night, I encourage you to look at. It's called The Formula That Killed Wall-Street.com, something like that. But it is the formula or the equation that killed Wall Street. And very long story short, again, I don't have all the time, sadly, but it's very interesting. They made this assumption, it was about something else in credit risk for the credit crisis. And the assumption was, it's worth actually spending a minute telling you about it, is that if you're all loans, right? Sorry, that's the way I teach. If you're all loans, you are not correlated with each other in normal conditions, if everything's going well, right? I mean, if Sam defaults, I'm going to pick on you because I know you slightly better than anyone else in the room. It's probably because he's had a messy divorce or that ugly drinking problem or whatever, but it's unique to him. That's the important thing. That's why he's defaulted. And so if you don't have to worry about it, or I don't have to worry about it if I've got all of you in my portfolio, if things are doing well, because he probably defaulted for an idiosyncratic reason. But if the economy is looking bad and he's defaulted on his loan, it may still be idiosyncratic, but the chances are that the thing that binds you now is not between you, it's that you're all connected to that thing, which is the GDP. Do you see what I mean? The GDP is, you get the picture. So it's not direct, it's not between you, but the fact that the GDP is, because so now he might not pay back his loan because he lost his job. And that's because the GDP is bad, and you're also connected to the GDP.
And then he has the risk.
And all those other requisite problems. But the point is, so correlations, I really shouldn't have picked on you. The correlation was set to 0. In that formula, that was a copula, You actually typed, I was working at Fitch at the time, you typed in, correlation 0. You set the correlation to 0 between these loans. And then, of course, the economy did turn bad, and things, there was a little pocket of, there was a reason. I mean, now suddenly there is correlation. When the market turns bad, people are losing great amounts of money, and because of the same reason, and there is correlation spreading through. And it was the formula that killed Wall Street. It was because that assumption, it works beautifully when the market is doing well, but when the market is doing badly, it super underestimates losses, and it wasn't the only cause of the credit crisis, but it was one of them, and it's a famous one. And we are super lazy in finance, believe me. So you make a normality assumption and this and that, and most of the time they work, but when they don't, it can be quite spectacular. So anyway, I don't have to tell you. The yield curve I spoke to you earlier, it's a big problem, how do we interpret it? And there's Stan, Nelson, Siebel, there's all sorts of interpolation techniques. But generally, you don't want a linear interpolation. So if you say to someone, I've got a cubic interpolation, it's marginally better, and that's just a mathematical one. There are other things which take finance and economics into account. But again, it's a physics principle that you can apply to these things. And I can see, I will finish on time. So just talking about the common filter now. And I didn't invent this, right? Obviously, I didn't invent the common filter, and I didn't think of this idea. I applied it, and I think it's just tremendous. I'm going to bore you with a few finance details. So there's the one dimension, there's your returns, and there's your excess, what we call market returns. So if you have a portfolio of stocks, and you have what we call the market, right, which might be the S&P 500 or the JSE, whatever. It's usually like the market. It's a whole bunch of stocks. And you regress, you collect a whole lot of data, and you regress what we call the excess returns, and they're called excess because you subtract off the risk-free rate. So what could I get if I put this money in the bank, right? And you may think, well, that's just a small amount. Well, of course, in South Africa, it isn't. So if I told you that your return on your portfolio in South Africa was 6%, you're not going to be impressed because you can put it in the bank for like possibly 7 with no risk, allegedly, or 10, exactly. But if you're in the UK, when, during whatever the interest rates are rising now, where the risk-free rate is like 1% and you're generating 4%, that's delightful, right? So you subtract off the risk-free rate. That's what they mean by that. So it's basically the returns on the portfolio versus the returns on the market. And if that was a perfect straight line, obviously then you are replicating the market, which is not very interesting. But that's the idea. So you want the slope on the positive side, these are negative returns. It's worth, I won't go on for too long. But so you get these returns over a series, you regress them, and you get the gradient, you get this offset here. And of course, this offset is when, basically when the market is returning nothing, your portfolio is still generating some number, what we call alpha, right? If you ever hear that buzzword, talk about generating alpha, it's a lovely buzzword in pubs in the UK. And it's when the market is doing nothing, you are still generating some sort of return. And also the beta, so they do use Greek symbols in finance as well. It's the slope of this line, right? And you want that to be higher. You want it on that side, so that when the market moves up 10%, if your slope is steeper, then your excess portfolio returns will be steeper, of course. But you want it to be shallower here, so you want a kink in this thing here, because obviously if this is a very shallow angle, then you lose 10% here, you lose 20% on the portfolio. There's whole PhDs in there, anyone who's interested. Okay, and this is what they do, right? The problem is you only get these return data every month. Stock returns, of course, are returned every single day, every second. You can go and look on Bloomberg every microsecond, they're changing. But in asset management, which is where this is used, because this is how you judge an asset manager. Are they doing well? Are they managing my money well, etc., etc.? So it is a big thing, because compensation in asset management is ridiculous. And so you go and you get, so these are monthly data, right? These are, now you can, I know, if you deal with data, okay, so one of those data points, it's not anyone's fault, but it's 36, it's already 3 years old. I mean, that was deep in COVID territory. Terrible time. And one of them is 35 months old, etc., etc. You get the picture, right? So, like, oh, is this still valid? Should you reward this portfolio manager who might have just been employed 3 months ago? So you've only got 3 months in there thing. How do you really wait for 3 years? But asset managers aren't going to wait, trust me. So there's all sorts of problems. You weight these things, you know, in time, the further ago they are, and that does improve things slightly, but it is an ongoing problem. You don't have a lot of data. You know, obviously more is always better, but then you're talking 5 years and 10 years, and like, is it even the same market? There's all those sort of things. Enter the Kalman filter. And along it comes. And in a nutshell, it really has to be in a nutshell statement. But you use the Kalman filter to say, okay, let's use, you use the real return data coming in, and it basically picks up the pattern, if there is one, and it learns. I've chopped off the learning part of this data, but it's all over the place. The Kalman filter, which is the red, yeah, it's the red line. It's while it's learning, what the blue dots are those regression values over time. So I'm just rolling it by 1 month. If you see what I mean, that's 36 months. And still, you're just rolling it forward by 1 month over time to see what this is the alpha, how alpha changes, and I use the whole series of stuff. And then you use the Kalman filter, and you can use the Kalman filter. And you can say, okay, you know, you can feed in the difference between what it forecasts and what the actual return is. And you might think, well, they look pretty similar, right? Let's, you know, why do you even bother? But just quickly, and this is just one that I drew up. I didn't draw it up for any particular reason. You can see here, the alpha is virtually zero if you use simple regression. But if you use Kalman, which has, it's demonstrably better, right? The R squared, the fitted values, it's demonstrably better. You can backtest the stuff and so on. It's giving you 2%, trust me, 2% excess return when the market is returning nothing is pretty substantial. So you would not be rewarding the portfolio manager here when you actually should be. And of course, at other times, works both ways. You know, they're only generating 2.5, but according you get the picture. So this is,
it seems like this Kalman filter gives you a different kinds of configuration periods
where things
just before it crashes.
So
Right?
yes,
So
yeah.
this is the dot-com bubble, and this is
Exactly.
the housing bubble.
yeah, exactly. And that may be another master's project or a PhD. I agree. And we also looked at beta, and I mean, I don't have to go, it's the same sort of thing. Beta, where's the interesting? Yeah, okay, got a little bit weird over here. But again, you'd be looking at a beta, you want a beta of like roughly 1. And over here it is, okay, they're not too different there, but here they are quite substantially different. You know what I mean? That Kalman is saying there's no beta, right? It's a flat. You basically, it's noise. Whereas, you know, if you're using regression, I'm just saying that Kalman filter can be applied to finance. That wasn't my idea. I would love to take credit for it. It's gaining more and more. I know they're using Kalman filters now in forecasting yield curves and all sorts of things. It's just tremendous. So that was a smattering. Don't worry, I will finish on time. Yes, I will. This is just to brag. I don't even know if I should bother you with this. This is a risk and return thing, and we had to figure out where this line, I really don't have time, sadly, to tell you what it was about, but where this line was tangential to this ellipse. If you know anything about efficient frontiers, it's an efficient frontier for a constrained portfolio. And I was rather impressed. I have a lot of students whose maths usually, because they've come from finance, is not as good as mine. Not that mine is great, but they thought of the idea, and they said, well, go on, figure it out. So I had to figure out the maths. But what we did was, you know what, I'm just going to show you the result because I don't want to go over time. But it involved partial differential equations and Lagrangian, it was just all that wonderful stuff, which you don't do often in finance. So when you do, you get a little bit of a cheap thrill. I mean, that was the equation. I should get the Nobel Prize for that. It's wonderful. But anyway, we figured it out, and I remember, actually, I will tell you this story. If my co-author is listening online, I had made a schoolboy mistake and I had got a minus somewhere. It's easy to do. There was a minus where there should have been a plus. And we plotted this thing, and you know, you could see the ellipse, and you could see clearly that's where the tangent point should be. And the calculated value was just slightly off. But you know, if you looked at it from an angle on 1 foot, they sort of aligned, and you could convince yourself, yeah, we've got it right. And my student said, but you've multiplied a minus by, people make these mistakes. You multiplied a minus by a minus, you got another minus. You should have got a plus. And I remember changing it to a plus, and it just clicked into a beautiful place. Oh, it was a cheap thrill. It really was. So sometimes you do have these odd projects where you can really get into some finance stuff. So the downside, I'll tell you about the downside in a second. Well, I'll tell you that now. is that I can't tell physics jokes anymore that my audience will actually laugh at. And I'll tell you this one, you've probably all heard it, but I still find it funny. The electron's traveling down this highway at 0.99, whatever, something quite precise. That's important, as we know. Speed of light, and he or she gets stopped by a policeman. Policeman says, do you realize you were traveling at 0.9936% speed of light? And well, 99.36. And the electron says to him, oh, great, now I'm lost. It's not the end of the joke. That's usually the end of the joke. Come on, physicists get that. Try and tell that to a non-physicist. Policeman walks around to the boot, flips open the boot, and says, do you realize there's a dead cat in here? And the electron says, well, now it is. Come on. Non-physicists do not get those jokes. So that's one of the downsides. There is an upside. I'm sorry, I don't think it's fair. The world is not fair. The amount, usually people say to me, so why did you make the transition? And I just say, oh, no, well, I'm not entirely a prostitute, but the money is ridiculous. It is, the seduction is, it's orders of magnitude. So I'm not going to deny it, right? But, oh, I don't even have my last few slides. Sorry, I've obviously got a later version here, but I took a photograph this morning and I just pulled out some random books from our bookshelf, which is no jokes. It is the good side of it, is that, it's not the same as practicing physics, right? Or dabbling in theoretical physics anymore. But you can still read. There's a tremendous amount of books out there, excellent books. And there's also some terrible ones. And if I had had the YouTube videos that that you have now, come on, students are spoiled. Now, you want to understand any concept, I don't have to tell you. You just Google it, and there it is. 4 blues, 1 brown, or 4 green. Is that you know the one? It's mathematical, beautifully visualized, like any concept you can think of. It's just it's a YouTube channel, and it's a mathematician, and he talks through, but it's beautifully visual. I think you want to imagine an electromagnetic wave. He's got it's just beautiful. And we didn't have those in my day. But I'm just saying, you can. I consider myself. I try to stay up to date with physics. Obviously your life doesn't, you never lose that passion. But as I say, you can be propelled into finance. You will earn a ridiculous amount more money, and I'll be the first one to say it. Don't think it's deserved. I really don't, but it's a fact of life. It's just a fact of life. You are closer to the money, as they call it, and so you see what traders earn, for example. But yeah, and the last point, that's Tokoloshe. Tobin's Q is just a performance measure, and it was a nice acronym, so thank you. Went 5 minutes over time, sorry.
No, thanks a lot. Any questions? Yeah.
You were in financial analysis for half the years approximately. Do you see a change in the culture and they become more mathematical in the last 30 years or still they're like?
Of course, you get super, phenomenal students, of course, in any field. And now with Python, where you can, my medium is Excel. It's so embarrassing. So I'm definitely becoming redundant. But modern kids, and ChatGPT, and I don't mean that in a bad way. I think ChatGPT can be a wonderful tool. And you just ask it things, and it can solve things. And of course, you get brilliant students coming out there. If you heard of, you probably have this, David Taylor. He was a Wits guy, and he broke away when he started a finance institute down in Cape Town, and he was from Wits. And the students he turns out are phenomenal, but it's by far the minority. The average student that's coming from a commerce background will know none of this. And I'm not saying they're stupid, they just haven't been taught that way to think. And it's very sad. Yeah.
Any other questions?
Yeah.
I'm sort of curious. From the day you left the UK facility, what was the sort of process like getting into finance? Because I'm thinking you had to probably convince people that you knew what you were doing, or how did you go into this physics knowledge?
Not at all anymore. If you say I've got a background in physics or mathematics or engineering, those fields, you will walk into a job. Honestly, the world has changed in that way. That people know now that these are people that will understand these things. I'll give you a very quick example. I work with RiskWorks, which is a little boutique consultancy, and we hired, and I really wish he was on the line because I'm going to really blow his trumpet now. He's a great guy. I mean, he's young. He's still got a tan, right? He's a youngster, but he's an engineer. He's come from engineering. While we were interviewing him, and this did not go down very well. The powers that be, who are all from economics and finance in my company, said, so, you know, you're coming from engineering, you don't know anything about finance. Why should we hire you? And he said somewhat arrogantly, but we've now subsequently learned that arrogance comes from deep confidence because he's a smart guy. And he realized that it was just a lot, it really is a lot of nomenclature and that sort of thing. And he said, oh, sure, I could learn that in 3 months. And that did not go down very well. And here we are, you know, maybe 7 months later, he is the top. He did not come from economics and finance at all. He's an engineer. He's a civil engineer, but no, mechanical, it's railroads and stuff like that. But he built the Kalman filter himself and stuff like that. And he is, sorry to the rest of you that are listening, he is streets ahead of any other graduate that we've employed because he's just very good at mathematics and finance. Not all of finance is mathematics. The vast majority of it is, it's pricing and it's understanding risk and, you know, and you can, if you get it wrong, you can, but anyway, to answer your question, it is extremely easy to get into finance.
But then why study finance at all? Why would anyone want to go into finance, do a 4-year or 3-year bachelor's degree?
Good point. I hope my boss in the School of Economics and Finance isn't. I mean, what is a bond? What is equity? What is a derivative? They're just words, it's just a definition. I'm not trying to poo-poo the damn thing, but you can learn that. You can learn that quite quickly. The underlying maths is the hard bit, and that's what you need to do. And so, yeah, it's a good question.
Right. So, okay, and this one that you've been trying very hard not to be disparaging. I will pick up that.
Good.
So it's already true. I mean, this is what Warren Buffett has been saying for a very long time now, is that you don't need asset managers. You shouldn't be paying asset managers any money at all because you just buy. That's been true since you've been able to have computers that are able to buy and sell stocks, like, you know, as they sort of come into that index, right?
At microsecond.
At microsecond. No, is it correct? In
Yes.
Switzerland, there's a law against actually there's a timing law, like, which is on the microsecond level. You're not allowed to buy stocks faster than that.
But it is
Yeah.
microseconds. I'll tell you another funny story about that later.
But the question is now, so is that was a sort of major technological advance that sort of came with coding and computers and so on. And now we are entering another advance in technology with AI and these types of things.
Yeah.
Do you foresee which finance job do you foresee collapsing next? Which is the next